Hello students, welcome to the course on Hydrology EVE 301, and let's continue our discussion on flood estimation and control. We have been discussing about the flood frequency method, and we have discussed about various distributions. So the one primarily used distribution is normal distribution, and we have discussed about it. And now let's go ahead and discuss about the log normal distribution. Now what happens is sometimes your data does not fit quite well in particular distribution. So in that case, what we do is we do a logarithmic transformation of the data set. Now how we are going to do is, now if you have a data, for example, your data series is like 5, 10, 20, 30, it goes on, okay, and you have realized that this value is not fitting in any distribution. So what we do is we then, let's say this is an x value, okay, so we then find the logarithmic transformation of this data. How we do is log of x, that is we do log of 5 comma log of 10. You do the logarithmic transformation of all the data set that you have, 20, okay. So likewise you do the transformation. Once you do your transformation, then you will see whether that particular this now the transformed data set is fitting in particular distribution or not. So now let's assume that it fits in a you have done a logarithmic transformation of your data set and it fits well in the distribution, normal distribution. Then our equation is going to be the frequency equation, as you have already seen, okay. This equation is going to be in this form now after doing the transformation. So it's going to be in this form. So it's going to be e raised to y of bar plus kt times frequency. So that's what is going to be our x. That x is the frequency, that x is the variable which we are interested to find, or the peak discharge which I normally use, okay. So after you do the transformation, you have transformed your data set, then your equation gets modified in this fashion, okay. Likewise, there are other distributions like extreme value distributions. So the extreme value distribution has three types of distributions, okay. This is type 1, type 2 and type 3. For such distributions, the kt value or the frequency factor is calculated in this form, okay. And there is another distribution which is the Pearson distribution. So if you do the logarithmic transformation of all the data set and you realize that it fits in a Pearson distribution, then we call it log Pearson distribution. It is commonly used distribution in hydrology, okay. So for log transformation Pearson distribution, the value of frequency factor is calculated by this equation, where k is the coefficient of skewness divided by 6. With this, let's do a simple numerical, okay. The question says a river has 40 years of annual flood record. So what we need to understand here is the data set is available for 4 decades, okay. The discharge values are in meter cube per second. Usually it is measured in meter cube per second. The logarithmic base 10 of this discharge value shows a mean of something like this. So what they are trying to tell here is, now they have already converted this into a logarithmic series, so which means they have done a logarithmic transform. So all these 40 years of data, they have calculated log of that particular values, and the mean is calculated as 3.2736 meter cube per second, and standard deviation is given as this much. The coefficient of skewness, okay, skewness missing here, skewness is 0.07. Calculate 50 years return period of annual series, okay. So 15-year return period, that value that we need to calculate. So like always, we note down all the value that is given. So all the values are given here, and we also calculated the probability of accidents. So probability of accidents is 1 by t, where t is the return period, which is 1 by 50, and it gives us 0.02. With this, now let's calculate our kt. So we know that kt is calculated using this equation. That very long equation is not mentioned here. Just understand that the kt has that very long equation, okay, frequency factor for normal distribution, log normal distribution, right? Somewhere it says it is now as such they have not mentioned about which distribution we have to use, so let's use by log normal distribution. So now what we do next is we find the kt value and we simply plug in that kt value in this equation. What we need to understand here is this y of t is what we have calculated is in fact it is this fashion that we have already seen, right? It is the x bar plus sigma kt. This yt is in this fashion because we have already done the transformation. So here our xt is going to be the value whatever we have got here raised to power 10, sorry, 10 to the power whatever value we have got here, 3897. So you are doing anti-log here, so from this we calculate our value. So this is the actual value. Okay, this is the actual value. Actual value in the sense this is the 50 years return period flood provided this property of the distribution. So that's how we solve the numericals. Now, as I said, the question has not mentioned about which distribution we have used, so we have just randomly chosen one log normal. Same thing can be done with some other distributions like log Pearson type 3 distribution. Here, the frequency, only difference is the frequency factor, right? The difference in different method is just the frequency factor. So for this log Pearson type 3, the frequency factor is calculated on this, and we have already calculated as 2.054189. So that is the frequency factor calculated. Okay, so this is the frequency factor for normal distribution, and for the log Pearson distribution the frequency factor is calculated like this. Okay, like always, then the y of t is equal to x bar plus standard deviation times kt. You have got this one, and the actual value is the x of t is whatever value you have calculated, right? 10 to the power whatever value you have calculated, and you're going to get this. So you can see the difference. Okay, same methods, it has to be, the value has to be somewhat similar. So from log normal we have calculated to be 7800, and from log Pearson we are calculating to be 8100. Not very different. Now this brings us to a new topic, and let's discuss about the risks, reliability and safety factor. So whenever we are designing some hydraulic structures, it is always, we have to be sure. Now there's always a risk associated with any design. So in a study over 300 dams, okay, it was found out that 35% of the dam were due to inadequate spillway. Now why? The reason, what we need to understand from here is why they did not design this spillway adequately is because their calculations were mistaken. They have not taken into consideration of the risks. So when they don't consider a factor of risks, then this kind of mishaps can happen. And what is in fact a risk, if you ask me, then it is simply the probability of occurrence. Risk is the probability of occurrence of a flood at least once during the successive years of design life. So let's take an example and understand this. Our Chuka Dam is designed, its lifespan could be 100 years, right? So it was constructed somewhere in 80s. So in next 20, how much? Now 80 plus 100 is going to be 180, right? So 2180. So in between, so it was, if it was constructed in 1980, it has a lifespan of, let's say, 100 years. So by 2180 it must be demolished. But the main reason that I'm bringing this example here is, what is the risk of this structure? What is the risk of this structure? You have constructed for 100 years. What if there's a huge flood that is coming, and what is the risk associated with this design? So that is what a risk means. Risk is the probability of occurrence of a flood. Now when I say risk, there's always associated with some values. Yes. Now this Chuka Dam, which is constructed for about 100 years of design life, must have been designed for some design flood. Yes, it could be 1,000 years return period. The concept here is, what is the chance of that 1,000-year return period flood occurring within this duration? So let's say our 1,000-year return period flood was 5,000 meter cube per second. So this is also known as the design flood, right? So to design any hydraulic structure, you need a design flood. So for Chuka Dam, if it was designed for 5,000 meter cube per second and its lifespan is 100 years, the question here comes, if a flood more than the magnitude of 5,000, if it arrives within this lifespan of 100 years, then it will destroy, right? So that is where RIX comes into picture. To calculate RIX, it's very straightforward, okay? The formula to calculate RIX is 1 minus probability of accidents raised to power n. So here t is the return period, okay? This equation is derived from binomial expression and it is like this. Now probability of non-occurrence, okay, probability of non-occurrence is 1 minus p raised to power n, where p is the probability of accidents, okay? Sometimes it is written as q. And why I'm saying probability of non-occurrence is, probability of non-occurrence is what we call by reliability. So probability of occurrence is RIX, probability of non-occurrence is reliability. Higher the RIX, lesser the reliability. More the reliability, lesser is the RIX. That is the connection between these two. Now, of course, the equation is already provided to you. You can also tabulate these values for quick access, okay? Let me explain this with the help of a table. So in this, in the green column, it is given the life, expected life design, okay? It is the expected design life of any structure. In this column, it is given the RIX factor. Now, what should be the return period of a flood that must be designed if you have to consider, let's say 15% of RIX? So if you are constructing any hydraulic structure that has a lifespan of 20 years, okay? Now please understand this. You are designing any hydraulic structure that has a lifespan of 20 years, okay, and you are designing for a RIX of 15 years, 15%. So what should be the return period of that flood? If you say, now this is going to be return period. Now if you calculate, the design flood should be a return period of 123 years. That's why in our class I have always said, for the most important structure, usually return period of 1,000 years is considered. Let me explain why we are considering 1,000 years is because for any structure that is going to be, the important structures are usually constructed for 100 years. Now why we are considering 1,000 years of return period is because the RIX is very less. Now if you see, it is coming 9,900 and okay, it's a 10,000 years, okay, sorry, it's a 10,000 years return period. So if the RIX that you are calculating is, you want to minimize the RIX, it's just 1%, and you're designing for 100 years, that structure you are designing for 100 years, then the return period of a flood, that you have to consider is 10,000 years. 10,000 years of return period flood if you consider, then the RIX is just 1%, okay? In another word, what we are saying is the probability of occurrence. RIX is probability of occurrence. Probability of occurrence of 10,000 years return period flood within the lifespan of any hydraulic structure, that is 100 years, right, is just 1%. The probability of occurrence of this flood, 10,000 years return period within the lifespan of 100 years is just 1%. So that is RIX, okay? So with this, I would like to end my lecture here, and there are some other informations. There's some numericals, you can go and check it out, and there are some additional informations I have provided here, okay? The design frequencies is just like, the discussion that we have in the class. So later on, there is flood control. There's a small section in flood control in this chapter, which I leave upon you for self study. Okay, with this I would like to end this chapter. Thank you.